webinars with Kenji Fukaya, who will tell us about asymptotic convergence of a holomorphic curves and disk bubble.
Okay, let me talk.
Not quite. Okay,
so the title is Growing Analysis and Asymptotic Behavior of Pseudo-holomorphic Curve with Bubble.
Sorry.
Okay.
Thank you.
So something I'm supposed to talk is about analysis and this growing analysis. And I talked with John last time that recently not so many people are doing this growing analysis, and most people like more than 40 or 50 are interested in growing analysis. But still there are something, and something I found is that I talked many things about this virtual techniques for a long time, and whenever I talked it, I am so busy about talking applications or things like that, and I honestly thought that I never talked about analysis about it. So probably this is the first occasion in these 15 years I talk about growing analysis. So maybe I'm getting enough old to talk. So. Okay, so now let me first explain which kind of problem I want to talk. So I mean, here just to do the complete generalities and kind of notation is one definition of the is some for blackboard. So it's a bit too much. So I just want to talk some particular case. So we consider X omega. J, X is a smooth manifold, omega is symplectic form, and J is almost complex. And we consider sigma I, maybe some marked point. This is the marked Riemann surface. So this is in the degree manifold, Gi and Ki plus 1. So Ki is the number of these marked points. And I just want to plus 1. And let me write it. This is in the interior. So this means that this is a smooth curve. And we consider Ui from Ci to X. This is a holomorphic, J holomorphic. And with the homology class alpha I. So now, what I want to study, so you have this kind of things, right? You have a U1, you have another U2, and let me assume that you consider U1 of the first marked point, Z1 0, is equal to U2 of Z2 0. So you fit these 2 points matches. So you have a nodal curve with just one singular point. And of course you can generalize the story up to the full graph of this, and you have as many singularities as you have. But as I said, that if you include so many singularities, then you are just too much notation. So I just want to consider this case. Then you consider this pair, sigma 1, sigma 2, joined this glued by this, and U1, U2, and this Z1 minus Z1 0, Z2 minus Z2 0. So this is an element of the moduli space with genus summed, and K1 plus K2, and homology class alpha 2. So this is the moduli space of pseudo-holomorphic curve with genus G1 plus G2 with K1 plus K2 marked points, and homology class alpha 1 plus alpha 2. So this is actually a kind of one singular point. And the growing analysis is supposed to give some coordinate of this particular point. So this is a bit too long, so I want to write it P1, P2. So I will write this as Pi. So you have a glued point. This is a particular point. So I want to describe some kind of a neighborhood of this point here. And that's a kind of what this growing analysis are doing. And usually one need to include some obstruction boundaries to make some smoothness. But again, it's just to make the writing shorter. I want to assume the following conditions. So we consider this linearizations of the operator of Ui. And that goes from the sections of pullback to the sections of pullback tensor to 0,1 form. And I want to assume that this is surjective. So this is I think this is something which we should not assume for the virtual techniques. But you can include some obstruction boundary to achieve this. And that is something quite different from what I'm going to talk, so I just want to assume this. And I want to assume also the following. We consider this kernel, du1, d bar, plus kernel, du2, d bar, and I want to let go to tx. So you have this kind of b1 and b2, and you take the value, it's here, at this marked point. You take sum. So we assume that this is surjective also. So these are two assumptions I want to make, and I want to study the moduli space here in the neighborhood of this P1 sharp P2 under these assumptions. And I will explain what is the problem and what is the kind of people concerns.
So you're fixing B1 and B2 now? Or is this
We fix U and U2, one particular point, so it's a local problem. And so we consider somehow the neighborhood of Ui in moduli space Gi Ki plus 1 alpha I. And then this neighborhood of Ui is smooth. This is just by this surjectivity set, yeah, by linearized equations, that is smooth, that is surjective. So the solution set is smooth. So let me write this Bi. Then we have considered this B1 plus B2, but the fiber product over X. Fiber product means that you have an element U here, then you take this value at this Gi0. Then you have a map from B1 to this X, and you have B2 to plus X. And this map is exactly the kind of tangent map of this fiber product constructions. And this surjectivity of the second guy implies that this is also a C-infinity manifold. So this particular thing is just a kind of a modular space of this singular object. I mean, this guy contains both smooth and singular things. And if you restrict to smooth singular things, you have this fiber product things, I mean, nearby. So you have this modular space. And then we want to consider its neighborhood. So that's
going to give you coordinates for the divisor.
Yes. Yeah, that's right, yeah. And this, the coordinate of this is kind of quite just a fiber product. It's quite obvious. And something people concern is how to kind of extend this coordinate to its neighborhood. So I want to take this. So let t be some positive number, and you have a theta on S1. And I want to use this in the following way. You have this sigma 1. Then I want to take this sigma 1 minus k1. This is compact. It is equal to 0 infinity cross S1. This is biholomorphic. And I need to say a bit more, because you consider this neighborhood Bi. So this sigma I is actually not fixed, but it's a kind of moving. This sigma bar is a kind of a neighborhood of this Deligne-Mumford, pure Deligne-Mumford modular space. You parameterize by this sigma I. This is a parameter. And then what I want to assume is the following. We consider this complement of the compact subset, which is independent of sigma, this parameter sigma bar, and we fix this biholomorphic map. So it's something like you fix a coordinate in the neighborhood of this zeroth marked point. And we also fix smooth parameterization of this sigma 1 sigma bar. This means that you have a trivialization of this Deligne-Mumford modular space. And of course, the complex structures, interior, may change, but you fix coordinate. You will see why I want to do this later. So this is the sigma, this is the descriptions. And you can do this for another part. So you have a sigma 2. You have a sigma 2 minus k2. This is sigma 2 bar. And then maybe it's better to say minus infinity 0 plus S1. So this is another things. And of course, this is biholomorphic. So now, I want to define sigma 1, sigma bar, wedge t, theta, sigma 2, sigma 2 bar. So let me write this for the simplicity. Sigma t theta, sigma bar. And this is given in the following way. We consider this guy. This is the sigma 1 bar, and you put this, here you have a K1. And you put some strip of this minus 10t. 10 is just by accident, I used in some place. Then you have this K2. So you fix this, you put this long neck in between. So you move t, you have a family of Riemann surface. And this theta appeared in the following way. This is, I think, called some Finter-Nielsen twist. I mean, you just do this, you have one parameter of freedom, you rotate this. So you rotate by theta. So if you just fix t and theta, you get this Riemann surface. And I forget the assumption. Sigma 1, G1, and the sigma 2, G2, this is assumed to be stable. So in general, we need, this is not stable, we need to fix extra marked points, but that's another story. So I want to fix both are stable. So this means that this t and theta is actually a parameter which is normal to these divisors. So you fix this t and theta. Then the claim, so the claim I want to explain here is 2. The first statement is the following. Let me write the theorem. This should be very old theorems. You have a phi which goes to this fiber product cross T0 infinity times S1 tilde. I'll explain tilde soon. To this G1 plus G2, K1 plus K2, alpha 1 plus alpha 2, and that is homeomorphism to a neighborhood of this glued object. So this is something like so let me explain tilde. So t theta is equivalent to t prime theta prime if and only if it is equal or both are infinity. You know that if this length is infinity, then this freedom of rotation just disappears. So this is the natural things. So what we can do is that we have this green constructions. You have this singular things that its neighborhood is parameterized by this thing. So that's the first statement. I think this is I don't know. This is at least 10 years old. I think 15 years old or something like that.
You say homeomorphism. Could you get diffeomorphism when you open these?
Yeah, so that's the next thing.
Okay.
So the next thing is the following things. So something I want to do is the following. The problem is if you see this, so this one is so T0 infinity cross S1 tilde. This is homeomorphic by some open ball, right? You have a cone, something like this, right? This S1 is shrinked. So this is homeomorphic to the disks. But then if you see by these descriptions, you know this smooth structure except this infinity. But then this highlights somehow all interval contains infinity. So the neighborhood of infinity is topological space is quite well defined. But as a kind of smooth manifold with boundary, then there are the choices. Which kind of smooth structure you choose at infinity. And that's something like, I think Helmut Hofer is so much concerned for a long time about these problems. And this is something what we do on this kind of things. Okay. So now for this purpose, I want to see this map, just using green map, and how it behaves when we consider t derivative of this map. And but for this, we'll take the following things. We consider ki is contained in sigma I, right? And then we also consider ki is contained in sigma t theta on this sigma bar, right? You have something like this. And then we forgot this part. This is something changing by t. And this part is k1 and this part is k2. And what is important is that this k1 and k2 come with fixed coordinate. You fix the coordinate of this. You have a single smooth manifold. Complex structure may be changing, but you have a fixed coordinate. So the theorem 2 is the following. We consider this phi of this law. Law is on this fiber product. And then t theta, and I want to restrict to k1 the K2 is the same thing. And then you take a derivative by t on L1 times, and derivative on theta on L2 times. And then we take this L2 m minus L1 minus L2 norm. So this K has a fixed, come with a fixed Riemannian metric. So you can put this Sobolev norm. And what's important here is that we can take this differentials. I mean, if you consider this sigma t itself, then t is a kind of depends on the space depends on t. So to take differential of the maps, you need to make some choices. But here we fix this everything on side of k1 and k2. So you can this doesn't make sense. And the main claim is that this has an estimate of Cm e to the power minus small cm and t, and if t is larger than some tm. This is an estimate. So this is a kind of asymptotic estimate claim.
What's the metric on the Riemann surface? I mean, you have this Riemann surface, and you have this family of Riemann surfaces along, so you're gluing them with one.
Yeah.
Is the metric the one that I'm seeing on the blackboard, or is it some?
Yes, the metric is just on ki is just fixed.
It's fixed metric.
Yeah, it's a kind of you have a trivializations, and it's compact and it's independent on t. Yeah, so you can just fix any Riemannian metric. It doesn't make so much matter. So this is the second claim, and I think we wrote this as a claim in our book, but I don't know if this how much proof it is. But we believe that the proof is enough detail, but some people do not say it's enough detailed proof. So one of the main purposes is to explain more detail of the proof. And why this is so let me explain. But before explaining the proof of this second theorem, I want to explain why this is good enough to get a coordinate. For every m, but t should be bigger than tm, which depends on m.
Yeah. And then you get those
Yeah. I think this is good enough to prove smoothness at infinity, right? Because this is, if m is big, so it's cm for any m. So.
Sorry, I missed. What were the indices? The L1 and L, is that L1?
L1 is you take L1 times derivative with respect to t, this length.
But what is L1? L1 is any?
L1 is any integer. But of course, this m is so L1 plus L2 should be smaller than m. Maybe minus 10, sorry. This Sobolev norm should not be so bad. So something like this. Okay, so now.
But the constants don't depend on L1 and L2?
Yeah, because this is just finitely many choice, so. Okay, so now, before explaining some idea of the proof, why this is good enough. So we consider somehow, you consider this P1 wedge P2, and then we consider its neighborhood, and if we have a map, it's this neighborhood in a. So we take this small neighborhood. Then we have a map from B to, first thing is this Deligny-Mumford moduli space. Cross this L2 space. So L2 M, let me write this M prime, right? M prime K1 cross L2 M prime K2. And you can easily see that this is injective. Because, on a singular locus, if you have a big compact set, then its restriction is injective by unique continuations. And the other part is just captured by this. So this is an injective map. And what this means that this image is a smooth manifold. Maybe, yeah. Basically, this theorem says that if you go to this divisor part, this part behave nice because it's a kind of exponentially small. So this theorem says that this is a CMPD submanifold, but actually I need to make more careful. What is careful is a CMPD structure of this Deligny-Mumford moduli space. This is a bit careful because you have this subspace, which is something like a divisor. This divisor, right? And this is the fold, the Riemann fold. And you have a point in the sigma 1, where the sigma 2 here, and you have divisors, which consist of the point with one node. And on this node, the smooth structure is very easy. But you have this kind of divisor. It's a kind of x. Then, somehow, this is local, so the neighborhood of x is something like x times this 2 disk. It's locally divisors. And this 2 disk has a kind of coordinate t and theta. So we need to, so what is this coordinate? So I mean, and this coordinate and the other coordinate coming from this map part should be some interactions. So we need to carefully choose this coordinate on this open disk so that everything is smooth. And there is an obvious choice of smooth coordinate. One obvious choice of coordinate is z is e to the power minus, I think this 10 is natural because I took 10, it's not important. 2 pi I, 2 pi I, yeah, I think this is something. Square root minus 1 theta. And this is a coordinate if you do everything in algebraic geometry. I mean, if you work in algebraic geometry, of course, this modular space with alpha and beta is, of course, a smooth projective algebraic variety, including this divisors. You have a natural coordinate algebraic geometry, and that is this coordinate because you have a very long neck of this length 10t, and this theta is something like this. So you want to make this and t and theta as a kind of complex coordinate, then this is a correct coordinate. And there is a paper by Robin, Luan, and Ditama Salomon, who shows that actually we can use this coordinate in the case when everything is integrable. If a complex structure is integrable, this z is actually a good coordinate, you get a smooth structure. But I am very much suspicious and almost sure that's not correct, that this is a good coordinate in the case of almost complex structure. So you use integrable structures, then basically the equation is linear in a neighborhood of each point. It's a complex structures. Your j is just constant, so your Cauchy-Riemann equation is just linear. So analysis is much easier. And in that case, it is good enough to use this coordinate. However, I don't think it is good in our coordinate. Then this looks rather strange coordinate is 1 over t e to the power 2 pi square root minus t. So this is our coordinate actually. And why this is good? So the precise claim is that we use this w as a coordinate here. It's not complex coordinate at all, just smooth coordinate. Then your submanifold is smooth submanifold. The reason is the following. So you have something like here.
I think hopefully use some different powers, something like that, but with different powers t.
Really? It's I think t of k or k is okay. I mean, so what we can use is the fact is something like what we get is if you take this dl c dtl something like that. This is estimated by constant power just minus constant t, right? So if you take this, this is something like absolute value of w. And so this is very much nice, right, with respect to this coordinate. It's all differential at origin is 0. It's too good. I mean, if you use this coordinate, then this estimate just means that c to the power z to the power c, right? And if c is an integer, it's a kind of polynomial, but the c can be very much general real numbers. So that's a difficulty here. But if you use this coordinate, then it's a kind of something which runs at the beginning of this smooth function. It's a kind of exponentially small coordinate. So it's okay. Yeah.
Is it clear that there is a diffeomorphism between these two smooth structures? Let's do the projective case and let's use this analysis and this gluing profile and that gluing profile.
I mean, identity is not a diffeomorphism, but I think you can make a diffeomorphism probably. You can just extend this. But yeah. I'm not so much sure because I'm not so much sure. Yeah, probably it's not true. Yeah. It's very nasty things to think, so I never tried seriously. Okay, so now this is something I want to do. So this is some. This gives us a way to give smooth structures on this exponential decay estimate. Okay. So now, No, so now I want to explain this, how to prove this exponential decay estimate. And there is actually 2 points. A is to do this growing in a L2M plus weighted Y2L norm, and using this coordinate, cylindrical coordinate on neck. I'll go back to this point, but if you see just many of the literatures in pseudo-holomorphic curve, this is not so much usual choice. I think most of the simplex geometry using this geometry use LP1, not L2M. And I think one reason is tradition. The other reason is what I heard is pseudo-holomorphic curve equation is equation of degree 1. So you don't need, there is no reason to have a higher Sobolev exponent. That I think is a reasonable way of explanations. But you may see that M is a kind of any big number.
Yeah, so, but I mean in this notation, M is derivative.
Derivative, yes. 2 is L2. Yeah. So this is a traditional simplex geometry. Then we just change it a bit. The reason, as I explain, but you have this kind of thing. So you lose it. So you take this M. That's one thing. And also we need to use this cylindrical coordinate. And usually people use just disks and remove it. But those are different. That's 2. And the other thing I want to explain is why. So what I wrote is something like this, right? You have a t derivatives of phi, and you have a L2m minus L. So why this minus L? You lose some Sobolev exponent by taking the derivative over L, t. They are, as you see, related. Because I need to take this L2m because we lose this L. And this loss of L is somehow related also something else which Kofa and those people mentioned. But anyway, so these 2 points I want to explain. And let me start with this second point. So what is the second point? So, I mean, I think it's completely impossible to start the growing from the beginning to the end. But I just want to show some basic part of the story. So you have a U1, which goes from this sigma 1 to x, and you have a U2, which goes to this sigma 2 to x, right? And what we know is that the U1, so yeah, maybe I want to first introduce some coordinate. You have something like this. And then in between you have something like a minus 5t times s1. So I want to take this tau is here. Tau is a coordinate, this first coordinate. This one has a coordinate tau. So tau is 0, is in the middle. But then, this looks too much technical, but there is something I need to say to write the situation clearly. You have this tau is 0. I want to introduce another coordinate. Tau prime is 0 is here. And tau 2 prime is 0 is here. So this is 5t. So tau is, what is this? Tau prime minus 5t. And tau 2 prime is tau plus 5t. Is this correct? I mean, I had a tau 1, tau 2, and the tau 1 is, yeah. So you have this. Why this is natural? Why I need to do this is a bit strange. But if you see this, you consider the sigma 1.
Tau is tau 2 plus.
Tau is tau 1 minus 5t. Tau 2 is tau plus 5t. No? Plus minus is different?
So one of the problems you have is that you don't have the tau 1s and tau 2s in the same spot. And look at the equations. They're not symmetric in tau. I don't know quite how to say it.
No, it's not symmetric. When tau 1 is 0, tau is minus 2t,
If you look at
5t.
those two equations, you get tau 1 equals tau 2. If you just look at the equations.
There you go.
Yeah. you are right. Okay. And then the tau 2 is tau 1 minus 5t. Right? No, 10t. Yeah, this is easy, but somehow So we consider this sigma 1. Then you have a k here, and I want to say that sigma 1 minus k1 is 0 infinity cross S1. So this coordinate should be tau 1, right? Because 0 should be here. And you have a k2. You have a sigma 2 minus k2 is minus infinity 0 plus S1, and tau 2 should be this coordinate. So this tau 1, tau 2 are coordinates which are associated on this sigma 1 and sigma 2. And what is important is that if you make t derivatives, then this coordinate should be fixed, otherwise it doesn't make sense. So now we have this u1 and u2 goes to x, then naturally, so u1 tau is infinity is equal to u2 tau 1. Tau 2 is minus infinity. This is p0. This is an assumption. So we want to glue, and before doing any serious functional analysis, you need to use some partition of unity. That's something like this: chi tau u1 minus p0, and chi this one tau u2 minus p0 plus p0. This I only want. So chi is some functions. There are many. You have a tau is 0. You have some partial unity like this. This is a chi this way, and you go to the other way, chi that way. So you use u1 in the neighborhood of this, in this side, and p0 is something like on a base point. And you use chi u2 here, and then you just write p0. So this is something like a so-called pre-gluing. Right? And then here we already have a problem. So I mean, if you go home, you have more. But this first step, you already have a problem. So you take this u1, u2, and t, and you want to take t derivative. And what happens? But of course, to take t derivative, you need to fix coordinate. So let me decide to use tau 1 and t. So this fixes the coordinate on a source. Then what's coming is this second term. So I want to do this more seriously. This is something like a partition of unity, but this is u2, and the coordinate of u2 is tau 2 and t. Right? So if you want to take a derivative, but you have to change this variable using tau 1. And tau 1 is here. So this second term is just became equal to this partition of unity u2 tau 2 plus minus 10t, tau 1 minus 10t and t. Actually, t is also somehow, you rotate this side and this side by this theta. So this theta appears like that, but just I forgot theta is 0. So now I want to take derivative of this guy by t. And this is first year calculus to see that maybe chi is everything else. So you take this t, then this is something like a minus 10 of chi of dd tau 1. No, I think better to write d u2 d tau 2, and we plug in here. Right? So when you take derivative here, you take derivative on this natural coordinate of u2. So t derivative just converted to this tau 2 derivative. So what we conclude is that if you try to estimate on this derivative on somehow in a kind of sigma 1, then what you get is something, but on this u2, what you get is this is L2m, but L2m minus 1, right? Because you lose 1 differential. So that I think is the basic reasons we lose these differentials. Or rather, I mean, this t is a kind of rather dangerous parameter because it is kind of domain changes so much, and all others you can just kind of rather harmless parameters. And this t and theta is dangerous. So each derivative of t decreases this sobre exponent by 1, and each differential of theta decreases sobre exponent by 1. So I cannot explain so much more, but once we have this, we have set up this scheme to prove this gluing analysis. using L2M, then you can plug in the same scheme for this study of the t derivative and theta derivatives, so that you have this loss is just a number. So that is the first point B.
I missed something very elementary early on in this discussion, where you added the two things up.
Yeah.
So you have two maps into this symplectic manifold.
Yes. Yes.
How are you adding them?
I mean, we assume that this value at Z0 coincides.
Yes.
And you fix a coordinate there. Then you take partition of unity. So you have a.
So you fix some Darboux coordinate.
Yeah. Something like this.
You're just putting in a net that's not necessarily holomorphic.
Yeah.
It's just smooth.
Yeah, it's just some kind of flat structure. You can just, this is just a partition of unity. So you have something, the U1 is very close to P0.
Yes.
And then you take U1 minus P0 and you take this partition of unity. And you have U2 minus P0, you have to take this partition of unity. Then this is very close to 0. And this is neighborhood of P0.
That wasn't what bothered me, it was that plus sign that I didn't understand. Well, any one, there are two of them.
So maybe if you want to feel more happy, this is better. Exponential P0 chi
Okay.
exponential inverse P0 U1 plus.
So use the Riemannian map.
Yeah.
Okay.
Yeah, this is more invariant way. Yeah. But you can use coordinates so that this is just plus or minus. Okay, so now this is somehow the basic reason why you lose this exponent. And by this reason, if you try to do every business LP1, then you will have a trouble. Because you want to take a derivative, then you lose LP0. Probably LP0 might be still okay. But then if you try to do this twice, you get the LP minus 1, you are definitely lost. So.
It's not okay if you have Lagrangian boundary conditions that you do LP0.
Yeah. So this is the reason you need to do it in L2M, big M. So now let me go to the point A. And yeah, I think LP1 is kind of most natural because he tried to do this borderline Sobolev analysis. Then L2M is not correct. So he tried to prove removable singularity. You need this LP1. And I'm not so much happy about LP1 because this Calderon segment estimate is very hard for me, so I never understand the detail of the proof, but it's certainly correct. So for this kind of delicate things, you need to LP1. And also, when I read this book by Donaldson and Kroheimer, they say that one place in gauge theory, and this is the single place they need LP something. And this is related to this kind of places, but they never try to use this weighted Sobolev spaces. And I think if you just do this, their gluings, using this L2M space, but with weight, then it works. So, but then, so I'll explain what is this L2M gluings. That's something actually related to something I was working on in gauge theory 20 years ago. So, but anyway, so I want to do this L2M gluings. And but we need weight. And but before explaining the why we need weighted Sobolev norm, it is rather easy to see because you have this sigma 1, and I want to use cylindrical coordinate. So you have a kind of 0 infinity S1 tau 1 t, and then Pseudo-holomorphic curve equation is of course du d tau plus square root minus 1 du dt is 0. And so you have a kind of, on the loop space, you have equation u to this square root of minus 1 du dt. And this is, of course, elliptic, but has a 0 eigenvalue. Of course, right? Because this is exactly the constant map with a kind of eigenvalue. And this is something like the reason that we have a fiber product. I mean, usually, kind of in the simplest case of this kind of gluings, you don't have a fiber product. You have just a kind of finite sum. But here you have a x. X is the value of this map at this node. So you have a kind of a fiber product type gluing problem. That's I think called the Bott-Moss type gluings. our situation is not a kind of a most function, but the bottommost functions. You have a critical submanifold, which is X itself in this case. Pardon? Oh, I see. But B is bigger because of more. Okay, yeah, most is more. I don't know. Okay. So now, so this zero eigenvalue is responsible for this both things, and so I mean it means that you just take this usual Debye operator. I mean linearization of pseudo-holomorphic curve equation. This is not Fredholm. So then the usual way is to put this weight, something like e to the power delta tau. But you just put the weight. Then this is not good enough because you just put the functions which with this weight goes to 0. Then it means that this side you have exponentially small. But you should allow that this boundary value move on this x directions. So the actual Fredholm theory is the following things. Let me write it C0 of this U1. This is a pair of B and small b, and B is a locally L to M sections on this U1 star Tx, and B is a tangent space of some particular point. So U1 tau is infinity is P0. And the condition is B minus B, sorry. So U1 tau is infinity is P0. And the main condition is you have integrations of B minus B, and sorry. You take a case derivative of B minus B, and you take square, and you take this tau C. This should be finite for any k. So this means that you have a fixed boundary value V, and the difference between this vector, this tangent vector with B goes to exponential order to this B. So this is the correct Fredholm problem. Okay. And C1 of U is I think it's W on this gamma on this U star dx and 0, 1. And in this case, it is a bit easier. You just take this weight. So this is another Sobolev space, and so I think this should be, if this is m plus 1, this should be m. So we have this Debye operator, which this goes to the C0 u to C1 u. This is a Fredholm. And you can easily see that this kernel is a tangent space of U1 on this B1. B1 is a moduli space of holomorphic curve. So that is a correct Fredholm problem. And then I need to explain a bit about this Tom Monofka's Meyer-Beatrice principle. That's also something like 20 years ago. Monofka, it's a gauge theory case, but it's applicable here. It's a Meyer-Beatrice. And in this case, it is a bit easier because we have assumed surjectivity. So that is the following. We have this U1 here, and we have this another U2 here, and in between we have this 10T strip. So let me write this U1 T U2. Then this is compact, so we have usual linearizations. No, yeah, U1, Du2, D bar. This is C0. Two, right? But then if we compare this, so if we compare this D bar and this sum, then this is actually not chain homotopy equivalent. This is a bit too big. And I need to somehow modify this a bit in the following way. That is related to this Maya beatrice. Maya beatrice in these situations goes in the following way. We consider C0 U1 plus C0 U2. It goes to T of x. This is, as I remember, this is the pair of B1, B1, and B2, B2, and Bi is actually a tangent space. Right? I mean, B1 and B2 is a large Bi is a sections of this pullback, and this small Bi is a kind of a boundary value. And so you can just move this to the B1 plus B2, and then then what is true is we restrict to this kernel. So this is like FF. You take this kernel F to this C1. And this, what Maya beatrice principle says that this is the homotopy equivalent. And this is a linear index problem. You can work out the details. Okay, so now this is about linearizations. And our assumption is exactly says that this is surjective. So our assumption is this kind of things. Kernel du1 d bar plus kernel du2 d bar, and this evaluation map T P0 x is surjective. This is a kind of second assumption we assumed. So this is surjective. So you restrict to this kernel, then this is still surjective. So this implies that this d bar kernel f. This is just simple homological algebra. This is surjective. So this in particular means that this complex after glued is also surjective. So usually for this both most gluings, if your two moduli spaces are individually smooth, it's not enough. It is smooth after glued. What you need is just these two individual things intersect transversely by the evaluation map, and that exactly corresponds to this business. So this implies that we under our assumptions we have this surjective linearizations. So we can start working on this gluing analysis. However, there is one more important thing is that this surjectivity is not actually enough. Why it's not enough? So this is surjective means the following, right? So this is surjective. Say about R, T, C1, this glued things, C0, so exist. So that this RT and this D is identity. This RT certainly exists. And what you usually is that you take this pre-gluings and you take this RT to have a kind of a linear, to have a, so we have a pattern of a unity gluing, you have an error term here, and you apply to RT to get to perturb your maps, and then you can just kind of Newton iterations to get the correct solutions. That I think is a usual implicit function theorem type argument. I think this goes back to Taubes 30 years ago.
Where are the estimates that show that it...
Yeah. So that is the problem. So the point is that the norm of RT goes to infinity as t goes to infinity. And you can see it's easy to see this because you have a very long neck, something like this, and we use this cylindrical metric. So you have a very kind of small fluctuations here. So you take the derivative, it's very small, but it's kind of the height is big, so you have a bad things. So you cannot expect that this right inverse has a bounded norms. And that is, I think, the main thing we need to handle in case if you want to use cylindrical coordinate for the gluing analysis. And the idea is the following. So we change the norm. The idea is we use weighted norm for this Ci, this after glued, so that RT is uniformly bounded. So I mean, something we need to do is just if RT is bounded in a way independent on T, then you can work out this Newton's iterations. Because the pre-gluing, error term of the pre-gluing is exponentially small, so you can just do these iterations. Of course, you need to work out some more estimate like a nonlinear term, but it's in this case like a routine. So the best thing is, the most important thing is how to get this norm uniform. And you know, it's rather strange because this domain of this space is compact. So it is kind of, even if you put a weight, the sovereign space itself is just equivalent. Because the two functions on the compact space is just bounded. But they are not uniformly bounded when t goes to infinity. So you have a kind of family of norms so that this uniformity is kind of assured. So now I want to explain what is norm. And that's I mean, once you see the norm, that's very natural. So you consider this sigma 1. And what the norm you put is that this e to the power delta tau. So you have something like this. And you have another sigma 2. Then I think it's power minus delta. I think it is 1. Tau 2, and its norm maybe orange. So the norm here is this. So you have you start 1 and you have exponentially grow. And here you have 1 and you have exponentially grow. Right? So now on the domain you can just try to imitate. You have a very long domain. You have here. You have here. Then you start from this norm. You start from this norm, and on this side you try to take this red norm. And in between you have this somewhere this tau is 0, and then you just interpolate them like this. So this is E delta on sigma t. Right? You start from this bigger and bigger, and you start from this bigger and interpolate. You can just take this. Right. So this is E delta. So I want to use this E delta to fix a norm. So let me write the precise norm. So let me write the C0 U1 blah 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 U2. This is just a space is equal to L to m plus 1 or L to m on this U1 sigma 1 sigma 2 U star dx. But then the norm, so you have a kind of B here. The norm L2 m delta norm is the following. So first on this compact part, you just use usual Sobolev norm. K1 plus K2. But then on this part where you change this where you glue, you have this minus 5t cross S1. Then you have a V minus V 0 0. Sorry, delta K V minus V 0 0, and then square, and you take this E, this function, and K is 0 to M, and maybe we need to fix this guy. This is a norm. So roughly speaking, on this right hand side you just use usual L to M norm. And on this left-hand side, you use also usual L to M norm. On the in between, you take this value here. So this is a kind of asymptotic value which doesn't exist, but you just take middle. You remove this point. So everything should be close to here in exponential order here and exponential order here. So you put this some weight. And if you use this weight, so I mean, the claim is that and C1 is simpler, and we don't have this B00. You can just do the same thing, but with this weight. So now the claim is you consider D bar, D U1, U2 D bar from the C0 with this delta, and C1 with this delta, there exists a light inverse such that whose light inverse is norm is bounded independent on T, and R on this is identity. So if you just change this norm by putting this extra weight, then you have a light inverse which is uniformly bounded. And the reason is somehow you see that this weight function is exactly the same weight function you get for the sigma 1, and this weight function is exactly the same weight function for sigma 2. So you can just use this usual cut and paste things, and you just see this effect, then you can just prove this. So now once we have this uniform estimate, then I think you need to take some more kind of analysis, but it's a kind of routine analysis. And then after doing this routine analysis, you get this gluings. Okay, so now this is about this gluing things. So I think I have 5 more minutes, so I want to say something more. That's somehow a bit more delicate things, but it might be better to explain it. So, yeah. So that's related to the following things. So I said that this theorem 2 implies this coordinate gives some natural coordinate. But let me remind you the following things. So what we do is the following things. For sigma 1, we fix some coordinates so that this is equal to 0, infinity, S1. And for this sigma 2, also we consider something, right? Then using this, if you fix this coordinate, you get a map. You have a map from sigma 1, d theta sigma 2. That is something like a sigma 1, k1 minus 5t, s1, k2. So this fixes a map from this t infinity cross s1 to m g1 plus g2, k1 plus k2, and you have an extra parameter w. W is just w1 just parameterized the sigma 1. So this is the parameter of sigma 1, and this is the parameter of sigma 2. So you have this embedding, and we use this embedding to have this estimate and to have this coordinate. And what one need to last thing I need to explain is this map. This is like the phi. Phi a priori depends. The phi depends on the choice of trivializations, k1 and the coordinate sigma 1 minus k1. Right? I mean, you realize the Riemann surface as a kind of a trivial smooth vector bundle with moving j, and you fix coordinate on this nodal point. And once we fix this, we get this map. But this map is not completely canonical. So the next claim is the following. We have a phi prime come from another map, another choice. So what I want to make sure is that these two, phi and phi prime, basically gives the same coordinate as I explained before. I mean, if you fix phi, you get a coordinate in the neighborhood of your moduli spaces. If you use phi prime, you have another moduli space. You have an identity map, and you need to prove that this identity map is smooth, including the corners. Then the main thing we use the following things. So you have a map. So phi rho bar t1. So you have t theta. So this is both the homomorphism. So you have something like this, right? Rho t yeah, s. This is mu theta, right? You have this kind of map S. So you have some change of coordinates. So I mean, you have a Riemann surface. Then you somehow change the coordinate in this node. Then this parameterization of this Riemann-Manifold modular space changes, and that changes this S. And the claim is if you take this derivative of S, so you have a very similar estimate. Two of this S, and this is estimated by C e to the power C t. So you have two different choices. Then the difference is again this exponential order. I believe that this is well known. You have a kind of some very good doctor students working on Tahimura theory. I think he can prove it, but we don't see any proof, so we just decide to prove it. But the proof is somehow the proof we have is again some kind of using Green constructions. Green construction is something like this. You have this kind of things, sigma 1 and sigma 2. You have another representatives. Then you have kind of a biholomorphic map B1 and B2. I mean, this is just identity map, but you have a different coordinate. Then you glue this B1 and B2 to get a map from this glued thing to the glued things. And then you try to glue, then you need to adjust the parameter t and theta. And this adjustment gives this coordinate change. But using this gluing, it's a very similar kind of gluing as I explained before. You can get this exponential decay. So together with this kind of estimate, this coordinate, you can prove the coordinate change is smooth. Okay, I stop here. Thank you very much.
Questions? Completely clear.
So say again, this thing is, as an algebraic variety, it's smooth in the neighborhood of this point.
Yes?
How does that smooth structure compare to the one you get?
I mean, well, this is kind of exponential of the other, a logarithm or vice versa.
So,
I mean, algebraic geometry coordinate is something like e to the power minus t. What we use is 1 over t.
so which way is bigger?
I think in this coordinate, everything gets easier to smooth.
The identity map from this one to the algebraic geometry one is smooth.
Yeah. But not vice versa.
But it has zero derivative.
Yeah. I mean, zero derivative infinite order.
Yeah. Infinitely.
Yeah, so this is a kind of nasty coordinate, but I don't know any other ways to.
Yeah, so can you make a comment why you don't think the algebraic geometry coordinates in the non-integrable case?
So the problem is if you, so I think I don't read, I'm sorry to say I don't read this paper by Robin and Salamander 1, but the thing somehow he tried to use this kind of things, right? Plus square root minus 1 du dt. Then if everything is integrable, you can just write this as a kind of Fourier mode. And then the Fourier mode is completely kind of separate, and then you can just see this what is the eigenvalue of the corresponding argument. And then you see that here long neck, you have a kind of, so you have something here, then you have a kind of element tau t here in a long neck. Then u on this part is something like just a kind of approximated by this Roland polynomials in exponential order near the centers. And something I don't believe is that this is correct. Because you have a kind of some nonlinear effect, which is a kind of J, mixed up J. So this di is, I mean, because I think what one can do is the first order is okay. But if you try to do the second order, the first order somehow mixed up with the second order, they can kind of, then at least I cannot prove it.
Some square root.
Yeah.
So this is some sort of distinction between almost complex structures and complex structures. I'm having trouble seeing.
I mean, the distinction is the complex structure. This equation is a linear equation, and the almost complex structure is never linear, even in the very small chart. So one need to work hard.
Did you compare what you're doing with what Hoffman does? So kind of it's very, very similar, right? So
I think I mean, we use this L to M, and to get this infinity structure, use the all M kind of simultaneously. That seems to be something very much related to what he's doing. He has a tower of Sobolev space. But I think we didn't scale only from this M directions. And my feeling is that Hofer also kind of scale from this P length of things. No? That's something. I never so much tried hard to understand it, but somehow that should be kind of. And another big difference is that we somehow study this equation concretely. And what Hofer's intention is to make everything in abstract functional analysis type settings. So I mean, if one try to make this to a kind of just a general framework where all Green problem come in, then probably it ends up with what they are doing.
Any other questions? Okay, thanks again.